Section 8.5 is a relatively short section. It's on polar coordinates, and we're not doing everything in this section. I'm kind of hitting the high points. You're used to working in the rectangular coordinate system or the Cartesian coordinate system, where you're given an ordered pair like 2, 3, and you think of this as an x and a y, and you say, well, from the origin you move over 2, and you go up 3, so it's x, y. Okay? So that's what you're used to. But the rectangular coordinate system is not the only coordinate system. It's probably the only one you've ever worked in. But the polar coordinate system, you still write ordered pairs, but the first coordinate refers to r. Think of r as pretty much like we thought of r before. And theta is an angle. Think of that as what we did before as an angle in standard position. Right? Standard position, positive angle, negative angle. Right? So I have to explain how this works, but so if you're just given an ordered pair, like I said, 2, 3, if you're not told what coordinate system you're working in, you may plot the point, incorrectly. So you have to know. Before, you never even mentioned it because you only knew one system. But here, if I give you an ordered pair, you have to be told what system you're working in. Now, the way we usually do polar coordinate system, and you can get graph paper for this, if you wanted to. You certainly don't have to. Right? You still have the x and y axes, but instead of marking tick marks for x and y to help you graph, here we do concentric circles. Concentric means, concentric circles are circles with the same center. So you do a circle of radius 1, a circle of radius 2, a circle of radius 3, a circle of radius 4, etc. So if you look up polar graph paper, this is what it looks like. Okay, and in polar coordinates, we call the center, instead of the origin, we call it the pole. P-O-L-E, the pole. Okay, so this is still, 1, 2, 3, 4, 1, 2, 3, 4. Okay, but as opposed to the rectangular system, right, you always are on the x-axis and y-axis, so the tick marks on the axis. Here we're not going to be necessarily on the axis when we're counting out. That's why we need the circles. So let me just plot some points in the polar coordinate system so you see how it works. Okay, now r, it says in your notes that r is a directed distance, okay, so we'll have to talk about what that means. So pi over 4, again that's radians, again that's 45 degrees, but standard position, pi over 4 radians is here. Okay, now imagine, the terminal side of this angle, right, pi over 4 radians would be here. Imagine that terminal side just going like that forever, like it does. Now, r is 3 here, so this says go a distance of 3 on that terminal side. So it would be 1, 2, 3, it'd be here. There's my point A, that I called A. Right? So you rotate through pi over 4 radians, and you go out a distance of 3 on that terminal side. So 1, 2, 3. So see why we have the concentric circles, because without that, how far is 3 far away? 3 away from there. It's hard to see if you just do it with the tick marks on the x and y axis. Okay, let's do B. And you could do the angle in radians or degrees. Usually you stick to one or the other, but I mixed it up here just to show you could do either. Okay, now where's 270 degrees? Again, standard position, right? That's 0 degrees. There's 90, 180, 270. So 270 degrees is all the way to here. Now imagine the terminal side of that angle going down this way. So if r were 6, for example, it's not here, but suppose r were 6, it'd be 1, 2, 3, 4, 5, 6. That point would be right here. If r were 1, it'd be right here. But notice in this example, r is negative 2. Remember, whenever we worked with r before, in our x, y, r stuff, we never let r be negative, right? That's why here it says it's not the distance, it's a directed distance. So when r is negative, right? So again, 270 degrees is here. The terminal side of that angle will be going this way. When r is negative, you imagine that side going back the other way, opposite direction, and you go up 2 that way. So 270 again is here. The terminal side would be here. If r were positive 2, we'd go this way. Since r is negative 2, you go from the pole backwards. So 2 this way. There's B. Which sort of ruins the 270, doesn't it? Because 270 was here, and you expect it to be here, the point to be here, but it's actually back there because r is negative. Okay, let's do another one like that. I've switched back to radians. So here theta is negative 3 pi. Well, remember 2 pi radians is all the way around. So initial side is here. Negative 2 pi puts me back to here. Another negative pi puts me to here. So negative 3 pi, the terminal side is here. Again, the terminal side of that angle would be here, but r is negative, so instead of coming 4 this way, we're going to go 4 that way. 1, 2, 3, 4. There's the point C. Okay, so that's how you plot. So if r is positive, right, just rotate through that angle and head out, and wherever the terminal side would be, notice I didn't draw it, but right, pi over 4, the terminal side would be here in the first quadrant, you go out 3. Where would that point A have been if this had been a negative 3? Right? If this had been a negative 3, instead of going out this way, I would have come down this way, and it would have been here, right? Opposite. So that's how you plot points. Now, something that's a little different in polar coordinates is, as opposed to rectangular, is that ordered pairs are not unique. For example, suppose I just gave you this point C and asked you to find a pair of polar coordinates for it. Well, couldn't I represent this point right here as not rotating at all, so 0 radians, or 0 degrees, whichever you prefer, and r is 1, 2, 3, 4? Wouldn't that be the same? Wouldn't those polar coordinates give me that point? Right? Don't rotate at all, so stay there. The terminal side is here, and move out 4. 1, 2, 3, 4. So that point C that I've drawn there, you could write as this ordered pair. You could also write it as this ordered pair. Couldn't you also write it as 4 to pi? Go all the way around 2 pi, terminal side is here, and go out that 4 direction. 4 in that direction on the terminal side. So there's an infinite number of ordered pairs you can write for a single point. In rectangular coordinates, that's not true, right? I mean, if I ask you what are the coordinates of this point C in rectangular coordinates, what would you tell me? 4, 0, right? 4 and 0. That's what everybody would say, okay? So for rectangular coordinates, for every point in the plane, there's one ordered pair that goes with it. For every ordered pair, there's one point that goes with it. In rectangular coordinates, that's not true. Certainly for every ordered pair, you get a point, but for every point, you don't necessarily get one ordered pair. So that's where polar coordinates are a little bit different. Now, often, a lot of times, if you're in one system, you want to convert to the other. So how do you convert between polar coordinates and rectangular coordinates and vice versa? Well, we already have the trig to do that, right? Let me just draw our standard picture. Suppose I have this point x, y in the plane. Again, I'm drawing in the first quadrant just to draw it. It could be anywhere. Again, what is this just screaming for you to do? What have we been doing all semester? We have a point in the plane, right? The terminal side of the angle, say, will go here. I don't know the rotation, but we made a triangle with a vertical line, and let me just call that angle theta in standard position. Again, it may not be acute. It could go around 100 times. And what did we call the distance from here to here? We called that r, and here's x, and here's y, right? So in polar coordinates, we need the theta and the r, and in rectangular coordinates, we need the x and the y. We've been doing this all semester, right? And we even know the trig behind it, solving right triangles, right? So what's a relationship here? So suppose I had rectangular, and I wanted to go to polar. So suppose you knew x and y, and you wanted to find r and theta. Well, how do you find r? We know how to find r, right? Remember, r was the square root of x squared plus y squared. So if you know x and y, we already know how to get r. And again, I'm thinking of r as being positive here. Remember, you can either make r positive or negative, so here I'm just making r positive, right? Now, how do you get this angle theta? Now again, I've drawn this as an acute angle, but what's the relationship between theta, x, and y? Well, the tangent of theta is, right, y over x, or opposite over adjacent, y over x. So if you know x and y, you can get r and theta. Now what if you have polar and you want to go to rectangular? Okay, so now it's the opposite. So you know r and you know theta. Well, just do your right triangle solving, right? So if you know theta and you know r, let's go back to our solving right triangle stuff procedure, right? I know theta and I know r. I'm saying I know polar. How do you get x and y? Well, how do you solve a right triangle? Right? You pick an acute angle and two sides, two of those things you need to know. I know two of them. So what if I choose y? Well, what trig function relates theta and y and r? That's sine. So sine of theta is y over r. And cosine of theta is x over r. Right? Cosine would be x over r. So if you know r and theta, you know r and theta, you know r and theta, you can figure out x and y. So we already know how to do this. We've done this before, we just didn't do it in this context. So I don't memorize all this. I draw my picture and just use stuff we already know. Okay? So, right. So the next example says, let's do an example of this conversion. It says plot the point -2 5 pi over 3 in polar coordinates, and then find the corresponding rectangular coordinates for this point. Okay, so this is polar. Okay, so, well, let's plot that point. Now, where is 5 pi over 3? Again, I'm in radians here. Think of that as 5/3 pi, or in my head, I'm thinking 1 2/3 pi. Where would that be? In standard position, 1 pi is here, so that takes care of 1 pi. And then 2/3 pi would be 2/3 of the way to here, which puts me over, about here. Oh, that's not very accurate, but that's all right. The key is what quadrant you're in, right? So 1 pi and another 2/3 pi takes me to there. So that's the angle 5 pi over 3. Okay. And I didn't put the concentric circles because I'm only doing 1 point. I messed up my picture here. That's 5 pi over 3, but what's r? R is -2. If r were 2, I would come 2 down this way, but r is -2, so I actually have to go back the other way. So let me go backwards here, and out here somewhere. I don't really have a scale. But where's 2? That distance right there. Okay, so now if I draw my picture, my right triangle picture, so let's figure out what's going on here. If this angle here is 5 pi over 3, I'm trying to find this angle here, right, the reference angle to help me solve the triangle, to find x and y. I need x and y right here. So I need this angle right here. Well, if this is 5 pi over 3, 1 2/3 pi, how much is this angle right here? Well, 2 pi minus 5 pi over 3, if you get a common denominator, that's 6 pi over 3 minus 5 pi over 3 is pi over 3. So this angle right here is pi over 3, right? 2 pi minus 5 pi over 3 is the angle there. Now, how does this angle compare to that angle? These are vertical angles, right? Those are the same. So this is pi over 3, which is 60 degrees if you prefer. Okay. So let me redraw that picture bigger so we can see it. I made it too small. So this is the triangle we're working with here. This is y, this is x, this is 2, and this is pi over 3, which is 60 degrees. So basically, we just have to solve for x and y, and there's your rectangular coordinates. So you could do what I did before and say, choose the acute angle and 2 sides and work it out. But we already know how to do the special triangle with this is our 30, 60, 90 triangle, isn't it? And notice hypotenuse is 2, wasn't that convenient? Hypotenuse is 2. Well, how big is this side going to be? Well, the actual length of this is going to be 1, isn't it? And this one's going to be square root of 3. Right, that's just our usual special triangle. 1, 2, square root of 3. Now, 2 is on the hypotenuse. If 2 had been over here, it wouldn't have been the special triangle. It wouldn't have been, the 2 would have been, the 2 on the hypotenuse makes that 1 and root 3. If the 2 were here, that couldn't be 1 and root 3, is what I'm saying. Right? Now, we have to be careful, though. I drew this picture, this triangle just out here floating in the middle of nowhere. But if you go back and look at the picture, remember, in this quadrant, x is negative. So the length is 1, but x is actually negative 1. So for those polar coordinates, the rectangular coordinates for that point are -1 square root of 3. Notice I didn't really use anything that we hadn't used before. Right? I plotted the point, and once you plot the point, now this was the tricky part, figuring out that angle, right? Because if 5 pi over 3, if the point had been here, what would you do? You would have found that reference angle anyway. So there's really not a lot of extra work, but once you find that reference angle, the angle here, you have to realize it's the same as the angle there because they're vertical angles. So just draw your picture and use the trick we've already used before. If this hadn't been a special triangle, suppose this had been, 20 degrees, go back to that right triangles, right? Choose an acute angle and 2 sides and then solve. Okay, so that's an example of conversion. Okay, let's go the other way. Here, on this example that we just did, it was polar coordinates to rectangular. Let's do rectangular to polar. So this is rectangular, 4, -2. And the problem says find 2 sets of polar coordinates for this point where theta is between 0 and 360 degrees. So the problem is specifically saying to give your answer in degrees. And they want 2 ordered pairs. So they want 2 ordered pairs in polar. So r theta, r theta. Okay, well, let's plot the point. Rectangular, right, 4, -2 is in the 4th quadrant. So there's my point. So if you draw your little triangle like we always do with a vertical line, there's 4 and there's -2. Well, so what do we need to write polar coordinates? We need the r and we need some thetas. Well, we know how to figure out r, right? R is the square root of x squared plus y squared. I'm not going to put the negative though, because the negative square would just go away anyway. So that's square root of 16 plus 4, which is square root of 20. And if you want, that's 2 root 5. I'm perfectly fine with the root 20. Okay, so r is root 20. Okay, so what's the other thing we need to find? We need to find an angle. Well, I think it's useful to find that first. Now, that's not necessarily going to be my theta, right? I'm just going to find the reference angle first. What should I call it? I'll call it alpha. Okay. Remember, the book is using prime for reference angle, theta prime, but I'm just going to call it something else. Okay, let's find alpha. So basically, what do I have here? I have this triangle like this. And I'm trying to find alpha, and that's 4, and that's -2. But remember I told you when you're trying to find a reference angle, ignore the negative sign. When you're doing the computation, ignore the negative sign on the side or you're going to wind up getting something weird. If you wanted to, you could just do it with the root 20. Right? Use the 4 and the root 20, and then you don't have that issue with the negatives. But suppose we haven't found the r yet, and we just have that. Well, right, look at the triangle. We have the opposite and the adjacent. Opposite and adjacent is tangent, right? So tan of alpha is 2 over 4, which is the half. So what's alpha? Well, alpha is tan inverse of 1/2. And they wanted the answer in degrees. Make sure I'm in degree mode, which I am now. So tan inverse of 1/2 is, I'm going to round a couple places, 26.57 degrees if you round to 2 places. 26.57. Now that's the angle right here. Right, now let's piece all this together and figure out how are we going to write this in polar coordinates. Okay, so what angle could we use? Well, could I just say, okay, let me think of it this way. Could I say r is root 20 and theta is negative 26.57 degrees? Would that give me this point right here? Well, r is negative 26. Sorry, theta is negative 26 degrees, so that would come down to here. And then r is root 20, go out root 20 down that terminal side. These are the coordinates of that point. Well, what's the problem? The problem asks for theta being between 0 and 360, and that's not. So this ordered pair in polar coordinates does describe that point, but it doesn't satisfy that. So we can't use that. Okay? So what can we do instead? Theta has to be positive, so we have to go around this way. Well, what if we went all the way around to here? See, now theta is positive, and then you could use r as square root of 20. So let's do that one. So r is square root of 20. Now what's the angle all the way around to here? Well, we know that that's 26.57, so it's just 360 minus that, isn't it? Right? All the way around 360, back up alpha, that will be the angle for my theta, right there. Okay? And what's I'm going to be lazy. What's 360 minus 26.57? It's 333.43. 333.43. Notice which is a positive angle, so we're good. All right, so let's check myself. 333.43 takes me all the way to here. R is positive, so you go out on that terminal side. Right? Now, the restriction here, ignore the restriction for a second. What if I went around twice and then stopped there? Right? So that'd be 333.43 plus another 360. Couldn't I say square root of 20 and then add 360 to that, which would be, what, 693.43 degrees? Right? So that would be twice around and then stop here and then go out root 20. This does give the coordinates of that point, but what's the problem? That's bigger than 360, so we can't do that. So we're coming up with lots of answers that don't work. Okay, but what could we do instead? Right? Remember, theta can only be in this problem between 0 and 360. If you go all the way to here, r is root 20. Well, what's the only other possibility? What if we let r be negative root 20? Then where's the theta we need to? We're going to have to stop here, right? We have to go from here to here. Because that angle for theta, normally r is positive, you go this way, but if r is negative, you go this way. So that's the only other way you can do this particular problem, is with this setup. Because of the restriction, you can't go around more than once, and you can't go negative. So the only way to hit this point is to go on this side and use r as negative. So if r is negative 20, negative root 20, instead of going this way, I go that way. Now, what is that angle going to be? Well, we just did this little logarithm. That alpha here is that alpha here, isn't it? Because they're vertical angles. So I need 180 minus alpha to get me to here. And I erased the original one here. Right, it was 26.57. That was my alpha. And so 180 minus that is 153.43. Okay, so notice 153.43 takes me to here, and then r is negative. Instead of going this way, you go that way. So those are the only two answers you can give. It's the only two that work. So one order pair r is positive, and the other order pair r is negative. Again, if this restriction hadn't been here, we came up with 4 different answers, I think. Okay? But again, the trig is stuff we've already done, right? Finding r and finding a reference angle. We've already done that. So that's not really anything new. The only new thing here is watch out for the r's. Now what about, instead of converting an ordered pair back and forth, what if you had an equation? So the next one says, consider the equation r equals 2 cosecant theta. Now here's an equation with, cosecant. Here's an equation with r and theta. Well, this is a polar equation. Let's convert this to a rectangular equation. So instead of r's and thetas, we want x's and y's. And then it says to sketch the graph. Now I'm going to go ahead and convert and then sketch the graph, because we know how to do rectangular x and y coordinates. Well, instead of messing with the r, let's think about when we had our picture a little while ago with our x and our y and our r, and that was our theta. What was sine theta? Sine theta was y over r, wasn't it? So what's cosecant theta? Cosecant theta is r over y, isn't it? The reciprocal. So let me replace cosecant theta with r and y. Yeah. Okay, so r is 2, cosecant theta is r over y. Now you may say, well, wait a minute. We're trying to go to x's and y's, and you still have r's in the problem. Well, let me do one thing at a time. Let me get rid of the fraction. Multiply both sides by y. You get ry is 2r. And then you have an r on both sides, and if you divide both sides by r, you get y is 2. Okay? So notice I eventually did get rid of the r and the theta. Y equals 2. Now what does the graph of y equals 2 look like? Well, you know from college algebra, y equals 2 is a horizontal line passing through 2. Yeah. Now there are some issues with domains here, right? There are values of theta for which cosecant is undefined, so I'm not really trying to get into that gory detail here, but just doing this conversion to get to y equals 2, you already know what that is from college algebra. The point of this example is sketching y equals 2 in rectangular coordinates is easy. We already know how to do that. It's very simple. Sketching that in polar by plotting points, a theta and an r, and trying to figure out what's a line, that's a lot harder to do. Right? So in this example, it's like, you really don't need to use polar. You're better off using rectangular. Right? So I converted to rectangular and then just sketch the graph I already know. Now in the next example, we're going to go the other way. The next one says, consider the polar equation r equals theta. And then change the rectangular form and then sketch its graph. Okay. Well, let me go back to the little picture. Okay. Well, all right, there's not much to go on here, but how is r related to x? Well, r is the square root of x squared plus y squared, so we can put that in. So I got rid of the r. Now what's theta? Well, remember we had a little while ago, tan of theta is y over x, opposite over adjacent, y over x. Well, how do you get theta by itself then? Tan of theta is y over x, so theta is tan inverse of y over x. Yikes. Right? Tangent of an angle is a number, tan inverse of the number is the angle. So we can replace the theta with tan inverse of y over x. Notice I got rid of the r and the theta and only have x's and y's. And from college algebra, what did the graph of this look like? Yeah, my guess is you didn't discuss that. Right? Y equals 2 is no problem. This is a problem. So I did convert to rectangular coordinates, fine, but it's not very nice at all. Here's an example to sketch the graph. I'm not going to do it in rectangular coordinates. That's a mess. I'm just going to graph in polar coordinates. All right, so there are some advanced students say, why do we have to learn this other coordinate system? I like the rectangular. Here's an example why. This is terrible. Okay, so that's one part of it. By converting to rectangular, we did that. Now to do the graph, I'm going to graph it with the polar. By just plotting some points. Now, I mean, it's silly to make a chart, but that's fine. Right, r and theta. Right. Well, normally when you plot points, you shouldn't just stick to integers, but I'm going to here. Right? If I do -3, -2, -1, 0, 1, 2, 3, well, r is the same thing as theta, so I mean, I really didn't need to do this. Right? R, so -3, -3, -2, -2, etc., 3, 3, right? The r and theta have to be the same. Right? So let's just plot these points. Right? Now, let me do concentric circles here. Radius 1, radius 2, radius 3. Yeah, let me put a 4. We'll see if we need that. All right, let me do these first. The 0, 1, 2, 3. Well, where's 0, 0? The angle is 0 radians and r is 0. So we're here at the pole. There's 0, 0. Now where's 1, 1? Now 1 radian, now you should remember what 1 radian is. Remember the definition of 1 radian, that's a good circle. The definition of 1 radian, right, was if, whatever radius this is, you need to intercept an arc with that same length, r. So what angle would give me a length of r here? Roughly, that's close, there. There's a picture of 1 radian. And remember that was about 57 degrees. Okay, so there's one, again, 1 radian is about like that. Right? So if theta is 1 radian, where does that put me? Puts me up here somewhere, and r is 1, so I come out 1 that way. So there's the point 1, 1. In polar coordinates, not rectangular. Now where's the point 2, 2? Well, if theta is 2, where's 2 radians? 2 radians is about here, and go out 2 units on the terminal side there, so 1, 2. Right, so 1, 2. Right, so 2 radians, and then go 2 from the pole. Now where's 3, 3? Now remember, pi radians is halfway around the circle. So the negative x-axis here is at pi radians, which is about 3.14. So 3 radians is almost to that axis, not quite, almost but not quite. So 3 radians puts me here, not quite to the axis, and then we have to go out a distance of 3, 1, 2, 3. Something like that. Now, I went ahead and put in the 4. Where's 4 radians? Well, 4 radians is going to put us where? Certainly in the 3rd quadrant. Roughly here-ish. 4 radians is here-ish. And then so 4 radians will take me to here, and then 1, 2, 3, 4. It'd be out here somewhere. So think about what this is doing. As theta gets bigger, r gets bigger. So the more you rotate, the further away you're going to be from the pole. So you see what's happening here. You're getting this spiral. Now notice I haven't done these points yet. We need to do these as well. Now where's -1, -1? So instead of doing 1 radian this way, we have to go -1 radians this way. But remember, r is now -1. So if theta is -1, If r were positive, we go this way, r is negative, we go this way, and you're just going to be back here. Okay? So the theta is actually down here, but r is negative, so you go the other way. Now where's -2, -2? Well, here was my 2 here. 2 radians was this way, so -2 radians is going to be this way, right? So 2 radians was to here, so -2 radians is going to be here. But now we have to go, r is -2, you have to go back the other way, and it puts you here. So you see there's some symmetry going on. And let's do the -3, -3. 3 radians took me to here, almost to the axis. So -3 radians comes this way, almost to here. But again, instead of coming this way, we have to go back that way. 1, 2, 3. So there's symmetry. And again, the 4 is going to be over here, right? So then the -4, -4, and so you have, oops, that. But it keeps going, right? It keeps, the more you rotate, the further out you get in both directions. This is called the spiral of Archimedes, if you care. Okay, so notice this wasn't that hard to do, plotting points in polar coordinates, but try to use a rectangular equation would have been a nightmare. So you can get some interesting graphs in polar equations that are hard to describe in rectangular. Now for the last part, I say use the calculator. I know not everybody has the graphing calculator. I'm going to refer you, for those who want to practice with the graphing calculator, I'm going to refer you to another video that I did for another class to show you how to use the calculator if you want. But I'm just going to draw these out for you so you can see what they look like. So r equals 4. Well, the graph of that turns out to be a circle of radius 4 centered at the origin. That's no problem. Oops. And that makes sense, actually. Because theta can be anything. So if theta is 0, r is 4, theta is here, r is 4, theta is here, r is 4, theta is here, r is 4. You get a circle. The next one here is r is 3 sine 5 theta. Okay, again, I'm going to draw this just to help me. This graph is trapped inside a circle of radius 3. So I'm going to draw a circle of say, of radius 3 with a dash line. That's not part of the graph, I'm just drawing that to help me. And the graph looks something like, again, you know my drawing is terrible. I already went outside the circle. That is terrible. But you get the idea. So this is called a rose. Right. So notice this is out of 3. That's out of 3. That's out of 3. Right. So it's a circle of radius 3. So the 3 shouldn't surprise you, right? And notice the 5. Notice I got 5 petals. That's a relationship here. So we call that a rose. That's a terrible graph. I'm sorry. Now let's do another one that turns out to be a rose. R is -2 sine of 4 theta. Right? This shouldn't surprise you because the coefficient is 2. This is sitting inside a circle of radius 2. Again, I'm going to put a dash line just to indicate circle of radius 2 here. And you would think, well, that was a 5 and we got 5 petals. That's a 4, we get 4 petals, but actually you don't. Oh, lucky me. You actually wind up getting double that. You get 8 petals. Okay, not bad. Not bad so far. Hey, that's not bad for me. So that's what that one turns out to be. If you were a kid and you ever did the spirograph toy, these were the sorts of things you got. Okay, the next one, this is also a rose, the one we just did. Both of those we did were roses. The next one is r equals 4 cosine theta. Now this one here, notice the ones we did basically were centered at the pole, but this one's not. Actually, this one winds up being a circle. There, so it goes from -2 to -2, and that's at 2, and it goes out to 4. So this turns out to be a circle as well, even though it's not just r equals a constant. But R equals a constant centered at the pole, and this one's over. So that's a circle. And then two more here. The next one is R is 3 plus 5 sine theta. Now this one is a little different. So it crosses up here at 8, and it crosses here at 2, and it does this, if I can draw it. So it's a loop within inside a loop. And I've heard people pronounce this so many different ways. I've heard people say it's a limicon, a limacon. Actually, the C is one like in a facade. I don't know the name of the letter in French, but you know it's the C with the little tail. So people call it limicon, limacon, limicon. So you know whatever. Okay, so that's it's a loop in a loop. And then the last one here is R is 2 plus 2 sine theta. And that, same flavor, is 4. It crosses up there at 4. But instead of making a loop here, it makes a little dimple. And it does that. And this is called a cardioid, like a heart. Again, you don't need to know the names of these things. I'm just telling you for your information. Okay. So that's what I want you to get out of this section. And I'll explain what video to look at if you want to learn how to put these in the calculator.